Good afternoon, everybody. My name is Rahul, and I'm a PhD student working with Samriddhi. And today I'm going to talk about chains and turbulent flows. So first, I'll start with just introducing what is preferential sampling. The panel you see here, just forget about the first A panel. Just look at B, C, and D. So these panels show some particles in a turbulent flow. The black dots you see are the particles, and the background flow is in white color. So these particles are characterized by their Stokes number. Stokes number basically tells you the inertia of the particles. Larger the inertia, larger is the Stokes number, and larger is the time taken by these particles to relax to the local velocity of the fluid. So you can see panel B has Stokes 0.16, then we increase it to 0.8 in panel C, and again panel D has Stokes number 3.3. So if you look carefully in panel B, comparing panel B with C, we have more vacant regions in this panel than compared to the panel B. This is because once we increase our inertia, all these particles, they are ejected from these vertical regions. So the vacant regions you are seeing have large amount of vorticity compared to the regions that are occupied by these particles. So once we have inertial particles, they will be ejected from the vertical regions, and they'll start populating the straining regions of the flow. That is where you see all these particles in black color accumulating. So this is what is known as preferential sampling. Basically, inertial particles will be populating the straining regions of the flow, and they will be ejected out of these vertical regions. So the question we ask is, what happens if, so all these particles are non-interacting. What if we make these particles interacting? So what effects are we going to see then? So then, so to this end, we start with a model of connected particles, connected inertial particles. So we just link these particles. So all these red colored particles or beads, these are connected by springs, and so these are fictitious springs. They are just there for they are just a mathematical artifact. It just represents the interaction between any two neighboring beads. So we consider two different models of these chains. First, the figure A has all the particles that are uniformly inertial. All the particles are identical. In this case, only one particle is inertial. Rest all are tracers. Tracers means this is the relaxation time. They relax to the fluid velocity instantaneously, while the inertial particles have some finite relaxation time. So what we do is we take a number of these chains. In our case, we took 50,000 of these chains. Each chain had 10 inertial beads, and we seed so we take a turbulent flow, generate a turbulent flow, and seed that flow with all of these chains. So then we start. The main aim is to see what the competition between this elasticity of the springs and the inertia of the beads, what combined effects or whatever the interplay is, what effects do we see after that. So to start with the experiment, we write the equations of motion for all these beads, and we can evolve all these beads in a background flow. But instead, what we do is, for our purpose, it is easier to write the equation for these springs or the separation vectors. So the equation that you are going to see would be the difference of the equations that would come from two neighboring beads. So just to move on to the equations, this is my Navier-Stokes equation that would lead to a turbulent flow and accompanied with this incompressibility condition. And in this flow, we'll seed all these chains. So this is the equation for the separation vectors, Rj. So basically, this is a very ugly looking equation, but basically there are three components. This is the first component that would result from the Stokes drag of the bead. Inertial beads, they will experience a Stokes drag. So that comes from this term. This comes from the difference of the spring forces. So any two neighboring beads would have spring forces acting on them. So this comes from the difference of those spring forces, and this is a thermal fluctuation that we apply externally just to ensure that if we have a stationary fluid, these springs don't collapse to a point. So just to have a finite equilibrium length, we apply these white Gaussian noises. That means we are setting some equilibrium length of the chains. So we have equations for separation vectors and one equation for the center of mass of these chains. So similarly, we'll have equation for the heavy-headed chain also. The model of springs, this spring forces Fj, is such that they can extend only up to a finite length. So Rm is the maximum length that we set externally. So once the length of the separation vector reaches Rm, it can no longer extend, and that sets the maximum length of the chain. So first we look at the case of 2D turbulence. So we are basically solving an Navier-Stokes equation on 2 pi cross 2 pi periodic box using with 1024 collocation points. And so these are all the parameters characterizing the flow. The main thing that we have to look for is this Stokes and the Weissenberg number. These two numbers characterize the chains. Stokes is characterizing the inertia, Weissenberg is characterizing the elasticity of the chain. So larger Stokes number means larger tau p, and that means larger relaxation time. Larger Weissenberg number means smaller spring constant, and then smaller spring constant means more extensibility of the chain. So larger Weissenberg number would mean that my chain is more extensible. So with these two parameters in mind, we move to the snapshots. So these are snapshots from our simulations. The first one is for non-interacting inertial particles. This similar panel you saw in the first slide also. So again, these red colored particles are moving away. So these are some vortices here, and so they have moved away from the vertical regions into the straining zones. This is for the non-interacting particles. For uniformly inertial chains, you can see they are closer to the vertical regions, but still clearly outside the vortices. But compared to these non-interacting particles, they are closer to the core of the vortices. If you look at the weaker vertical regions, they are somewhere they are occupying the vertical regions as well. Just for the heavy-headed case, where only one bead is inertial, rest all are tracers, we see that the tail of the chain, that is the tracer part of the chain, is trapped into the vertical regions, and the head bead, that is colored in red, is trying to move out of these vertical regions, but because the rest of the chain is trapped into the vortex, they are forming a ring-like structure around the vortices. So this is all of this explanation that is going on is based on this extensibility of the chains, and whether what regions of the flow are these chains occupying. So first of all, to quantify this, we come up. So there is an Okubo-wise parameter. So Okubo-wise parameter is basically omega is my vorticity, sigma is my strain rate. So larger vorticity would mean I will have a positive lambda. That is the Okubo-wise parameter. And larger strain rate would mean I would have a negative lambda. And this mean of omega square is the entropy, and is just a normalization constant for this flow. So and we measure this lambda at the center of mass of the chains. So so looking at the plots, so these are all PDFs, probability distribution functions of lambda c for different Stokes and Weissenberg numbers. I hope this is visible, but anyway, I'll say it. So for small Stokes, that is small inertia, in the first panel, Stokes is 0.14. So the inertia is small. Now, if we look at, so for the first Weissenberg, when Weissenberg is 0.07, the red curve is actually here, it's not visible clearly. When Weissenberg is 0.35, still overlapping on this. But as I still increase Weissenberg over 1, so this is 1.38. So Now, because I've increased my Weisenberg number, the Stokes is still small. So the chains, the inertia is not strong enough to pull these chains out of the vortices, but the elastic nature of these, because these chains are now much more extensible, once they get trapped into the vortices, they pull all the beads together into the vortices. So for larger Weisenberg numbers, there is more tendency for these chains to be trapped into the vortices, and hence we have a very positively biased PDF for lambda c. And now, if I increase my Stokes number, now I'm increasing my inertia. So inertia will lead for these chains to go out of the vortices and go into the straining zones. And straining zones have negative value of lambda. So now, when the Stokes number is increased from 0.14 to 0.85, the positive tail gets thinner and thinner, and it gets more symmetric about 0. And still, going further, when Stokes is 2.84, we see that the trend continues and they become more and more symmetric about 0. So this is the case for uniformly inertial chains. There are similar plots for heavy-headed chains. So for heavy-headed chains, when we look at the plots for heavy-headed chains, so a very small Weisenberg number means the chains are not extensible, means that they are really acting as point particles. So the black curve, there's a black curve here that is there for non-interacting particles. So you see, when the chain is almost inextensible, they are overlapping with the non-interacting particles because the whole chain is condensed at a single point. But when I increase Weisenberg to 0.35, these chains. So when I increase Weisenberg to 0.35, the chains are now extensible and they are getting pulled into the vortices. So now we have a much more positive bias for this PDF of lambda c for heavy-headed chains. But I'll skip this with the interest of time. But we can come up with we have similar explanations for this and this plot also. So all these things that I said were because the chains were actually extensible. So when we look at the plot of these chain lengths versus Stokes, the red curve is for smallest Weisenberg number. So we can really see that for the smallest Weisenberg number, however large the inertia is, the length of the chain is almost flat. It doesn't change with inertia. But as I start increasing the Weisenberg number, I move up. You see the length of the chain is now really increasing. In this panel, we have the interbead separation of the chains. That is the length of a single chain of a single spring, and we see that for the small Weisenberg number, they are again distributed. They have a Gaussian distribution about their equilibrium length because they were being set by the thermal fluctuation that we have initially put in. And again, increasing Weisenberg number, they start to peak at around their maximum possible length. So this was the case for 2D turbulence. So for 3D turbulence, we do a similar study. This work still in progress, but now here there is a quantity called Q that is similar to the Okubo-Weiss parameter. Negative Q means straining region, positive Q means vertical regions. And we also look at the settling velocity, that is the how is the settling velocity changing in a turbulent flow. So we have similar plots for for lambda. Just we had for lambda in 2D turbulent case. We have similar plots for Q here, and I'll just skip to this settling velocity. So settling velocity, the plot is for delta V, that is a fractional change in the settling velocity compared to when a particle is settling in a stationary fluid. So we are looking at the fractional change in the settling velocity. So the Froude number here that is written is actually telling you the effect of gravity. Larger Froude number means smaller gravity. Larger gravity is smaller Froude number. So we see that as we increase the inertia of these chains, there is always some point where the change in settling velocity is peaking. So in that range, really, in a turbulent flow, we can say that the settling velocity actually increases, which to me was very counterintuitive initially, because a turbulent flow, I would think, would throw away the particles in all directions, but really it enhances the settling speed in the direction of gravity. So I'll just end with this slide. Thank you.
So as we are running out of time, so we'll have only one question, quick question.
A chain of tracers would get trapped inside a vertical region, because now tracers would just populate the flow uniformly, whether vertical region or a straining region. Only inertial particles would go into the straining regions. If you take a chain of tracers, because now these chains have the ability to extend, once they enter a vortex, they just get pulled inside the vortex and they stay there, because there is nothing countering the elasticity of the chains. The heavy-headed high, because it's an inertial particle that would try to pull them out, but the remaining tail was tracer. So there was one head bead. So in this case, so there is one inertial bead, rest all are tracers. So this one was trying to move out of the vortex, rest all are being captured. So so mostly the snapshot that you saw, the inertia was not enough to completely pull it out. So it formed a ring-like structure around the vortex.
Okay, so you have any further question, you can catch him later. So let us thank the speaker again.